So, thank you very much. And I'd like to show you some results of recent simulations of core collapse with rotation of magnetic fields, subtitle, Trying to Avoid Disappointing Michele. And right. Of course, this is not work I've been doing alone. I'd like to stress collaboration in Valencia with Miguel Angelo and our group, in particular also student Marco Cusinato, and all the computing time wasted in different Spanish supercomputing centers. First, let's start with an introduction. Why should we consider magnetic fields if, as we probably believe, the next galactic supernova to be detected in gravitational wave will be more a standard neutrino-driven one? Well, first of all, we should hedge our bets. We know that even in case of standard neutrino-driven explosions, there is a magnetic field very likely as pulsars come with magnetic fields, and magnetars in particular. We know of young neutron stars with magnetic fields of more than 10 to 14 Gauss, which may or may not have an impact on the explosion mechanism. So their birth fractions is not truly negligible. 10% or so of all young neutron stars may come with such strong fields, so better to consider them. Additionally, we've seen that the increasing number of realistic 3D supernova simulations performed for long times, for example, the ones by the Princeton group, show a wide range of explosion energies. Still, magnetic fields may or may not be required to go beyond that. May or may not. So you may or may not agree with me on that. But of course, there are many open questions in the field of magnetorotational core collapse. For example, we'd like to get unique, unambiguous observations of the presence of magnetic fields, strong magnetic fields. Therefore, we're going to search for characteristic observables in, for example, gravitational waves or neutrinos, or later in the electromagnetic emission that's driven partly by the elements formed during and before and distributed during before collapse. So we have to also consider the thermodynamics and the nuclear synthesis. I'd like to mention, of course, that this is by far not the first study in this direction. We have had many very beautiful magnetorotational core collapse simulations before that. Still, there is the task to unify this picture in a sense and try to figure out which of these different results, for example, in terms of the in terms of the geometry of jets that develop, or in terms of explosion energies, nuclear synthesis, and so on, are common, and which ones are due to the numerical settings. And as Håkon also mentioned, we are struggling with the progenitors. That's a field I won't go into. We can perhaps talk about this later. We are dealing still mostly with 1D progenitors. We should go to where in directions as, for example, the one outlined by Håkon, but also by Bernhard and Vishnu a few years ago, of performing 3D progenitor simulations. There's a lot of work to be done in that field. And our contribution here is a set of 3D core collapse simulations with magnetic field. Here I'm just summarizing the method, the numerical method, including a multi-D M1 transport scheme. We're running in 3D spherical coordinates. And with all that it entails in terms of complications in time step restrictions we are going around. Now, I'm going to show you results of essentially two different sets of progenitors. One, a little bit older set of models is for a single progenitor of 35 solar masses, 0H main sequence, which has lost about 7 solar masses by the time of collapse due to winds, has a relatively compact core, and comes with a magnetic field and rotation from 1D stable evolution. It's the model 35OC run by Woosley and Heger 20 years ago now. Additionally, a bit more recent is a set of in our case, 8 stars from 5 to 39 solar masses by David Aguilera-Dena and the group of Norbert Langer now 7 years ago. Also spherically symmetric stellar evolution, including the effects of rotation and magnetic field in the approximation of the Taylor-Sprout dynamo. A particular feature about this model series is that due to the assumption of strong rotational mixing, they evolve in a chemically homogeneous form during much of their evolution time. In the publication from 2018, David and collaborators estimated what kind of final fate these stars might have. From 5 to 39 solar masses, which is this range, based on the structure of the pre-collapse models and a few additional assumptions, they found that these stars might retain enough angular momentum to produce either superluminous supernovae or gamma ray bursts driven by protomagnetars or collapsars. The smaller masses, 5 and 8 solar masses, type 1c superluminous supernovae, and the more massive ones should produce collapsar GRBs. And in between, there's a window for protomagnetar-driven gamma ray bursts. Now, simulation results. Let's start with these 35 solar mass stars. There are 4 of them. They all have the same rotational profile. Rather rapid rotation. The magnetic fields we varied in a sequence from weak to strong with the model we nominate O for original, retaining the magnetic field that's coming from stellar evolution, which is relatively strong, perhaps not exceptionally strong, but already quite strong. In all 4 cases, we get explosions, as we show here in this evolution of the maximum shock radius. Explosions set in between almost immediately for the strongest field case and around 300 milliseconds after bounce. The explosion energies shown here in these solid lines go up to beyond 10 times the canonical value of 10 to 51 ergs for the strongest magnetized field. In the other case, we are at between, well, 0.5 or so of that value of a beta and 2 times that. The explosion geometry of the weak field case, which actually isn't all that weak, but still dynamically it's not very important initially, doesn't look very different from a pure hydro non-rotating star. We get very an explosion morphology that's dominated by very large bubbles. What I'm showing here are contours of the entropy. The highest entropy is in the form of these outflows, which are not exactly at 100 degrees from each other. They don't carry a lot of energy. They are subdominant. They are not the mechanism exploding the model, but we get such a jet component later on. If we crank up the magnetic field, we get, in fact, the familiar pattern of bipolar jets, quite strong and rapid, not really subject to the very prominent non-axisymmetric instabilities we've seen in other simulations. And to mention what Matteo did on the same subject, by varying the magnetic field geometry initially, for example, to quadrupolar instead of dipolar fields, you can get anything in between a more roundish for no magnetic field or a tilted dipole to quite jetted outflows later on. And that's the first set of models. And I'd like to mention the second one, the chemically homogeneous stars. In axisymmetry, they all explode. We have 8 stars. Shock runner, the shock revival, there's no prompt explosion in this case, like the very strong magnetic field before. But shock revival sets in between 100 plus milliseconds and more than 1 second after bounce. The explosion energies can be, well, relatively high, not as strong as before. And due to the assumption of axisymmetry, all the explosions look very bipolar. But of course, that's not what we expect in 3D. Now here's the set of 3D simulations. 8 stars, some of which have been run for reasons that are more to do with my chaos than physical reasons, sometimes in 2 versions. We have simulations of up to 3 and 4 seconds. All of them explode. We have a group, again, the group of low mass stars, 5 and 8 solar masses, explode only after more than a second, whereas the others explode between, say, 2 and 5, 6, 700 milliseconds after bounce. Explosion energies, this panel, are somewhere in between, well, half a beta and 2-point-something beta, with, in one case at least, a relatively late rise, even though many of them are relatively well saturated already after 1 second and a bit more. Representative cases, again, a more roundish bubble-like case for a relatively weak magnetized simulation, jetted, though not as strong as in the cases before. Explosions for in this 13 solar mass star, and the one star which forms a black hole actually shows probably the most pronounced jet-like explosion that we have among them. Now, we explored several correlations between compactness and explosion energy and so on. So if you look with the enough tolerance for error bars, you probably can see something like a weak correlation there. In terms of the proton-neutron star properties, as I mentioned, there is one case with a black hole formation. The mass of the proton-neutron star, which is plotted here, goes beyond, well beyond the stability limit. There's a lot of rotational energy, more than 40 times 10 to 51 ergs, which stabilizes it for some time. In other cases, the proton-neutron star growth levels off below, or in one case actually pretty close to the limit of our SFHO equation of state. So it may or may not later on yield black hole collapse. And if we look at this, at the time evolution of one such proton-neutron star, I'm showing you that because it's very relevant for the gravitational wave emission. What you're seeing here are profiles of radial profiles at different times of various quantities. In this case, the deviation of the radial velocity from its angular average, which means high values here indicate turbulence or convection. We have a very persistent convective layer around 20 or so kilometers, which is the proton-neutron star mantle that Bernhard introduced yesterday, situated somewhere between density contours of 10 to 14 and 10 to 13 grams per cubic centimeter. Outside of the contracting proton-neutron star, at some point the explosion develops, which is turbulent and manifests itself here in these high values of this radial velocity. We have rotation, as differential rotation, which has its peak around the lower radii of this convective layer, and the magnetic field as well. Toroidal and poloidal and toroidal magnetic fields are strongest below or at the bottom of this convective layer. Important point to stress here is how long this convection is operating, which we will see in the gravitational wave signals. Just to give you a few gravitational wave patterns. This is the emission of one of the 35 solar mass stars, the weakest one, and its spectrogram. We have relatively strong emission, and some of these typical features: a bounce signal, rising modes that reach, in this case, around 1,000 Hertz. For the more jetted models, which we're showing you here, apart from the stronger bounce, there is actually a weaker high frequency features. Now, for the new set of, I'm going to show you the results of these new set of 3D models. In each case, on the left, the signal for the two polarization modes in equatorial and polar line of sight, and on the right, the spectrograms of the characteristic strain for polar and equatorial emission. In many cases, we find over a relatively long period modes, sometimes one, but very often two modes in the 500,000 Hertz window. For example, here in this 8 solar mass star. Sometimes there is a rise, a stronger rise of the high frequency feature, in particular here for this black hole forming star. But very often we find this quite long emission at 1,000-ish Hertz. Depending on how bipolar the explosion is, we get a low frequency memory pattern, or not, depending on the conditions. But as I said, this long emission is there quite commonly. In terms of multi-messenger emission, I'd like to introduce a few neutrino light curves. Of course, in all cases we have the first bounce peak in electron neutrinos, but we can have a quite sustained long time emission of the relatively heavy proton-neutron stars at relatively high amplitudes and with all flavors at similar levels. In the black hole forming case, that goes down relatively quickly, but for persistent proton-neutron stars, it's more constant. A study we've participated in was trying to find out whether such neutrino emission with such characteristics could be actually close to the improving detection or non-detection upper limits for the diffuse supernova background. What can be in particular helpful here is if there's long time emission, and the emission of the neutrinos has relatively high mean energies, which can be the case in our compact course going towards black hole formation. So we are not there yet if we compare what folding in population synthesis and our results. If we compare that to the detection thresholds coming from Super Kamiokande, we are not there yet. Could be at some point helpful to reconsider that. Finally, to close the multi-messenger part, there is, of course, if we want to say something about the electromagnetic emission, we have to consider the nuclear synthesis of these models. We've done so far with the set of 35 solar mass stars, including also the ones performed by Matteo, using the nuclear reaction network WinNet, in post-processing based on Lagrangian tracer particles with more than 6,000 isotopes. And one of the pressing questions, or tempting questions at least, for magnetorotational core collapses is whether there is or is not an OR process for giving us nuclei beyond at least a mass number of 100 or 150 second, third OR process peak. Well, we don't necessarily get a very robust OR process peak here in axisymmetry or in the 3D results. Only for the strongest magnetic fields, we go somewhere around in 3D results. Here, the blue lines, somewhere towards the A equal 200 mark. Other than that, well, there is a weaker OR process which still could be interesting for nuclear synthesis in the early universe, early galactic enrichment. Whether or not that's more relevant in the current chemical composition of our Milky Way is a different question. Still, we're going to address this question also for the more recent set of chemically homogeneous stars. And that brings me to the end. I'd like to just mention that this whole enterprise is going to be called the Molbet catalog and is hope to be released sooner or later. Thank you very much for your attention.
Thank you, Martin. So you have time. So first, Chris.
Martin, excellent talk. I have a question on the gravitational wave signal. Ori Gottlieb was seeing some Rossby wave modes in that disk of this rapidly rotating star. Do you actually see that as well? And what is the feature that I should be looking for if I'm seeing a Rossby wave?
Right. Well, perhaps in that respect, one of the closest case could be that it's not the weakly magnetized to the 35OC star, which I didn't leave the plot in, produces a very flattened protoneutron star. And there, if we look at the spectrum, we can identify as actually two phases in the evolution. One in which this high frequency feature, which is not that high frequency up to then, rises slowly. And then there's an intermediate phase in which it starts rising faster and actually splits into different modes. So that might be It's not exactly the same, but could be an interesting feature of such a very flat and.
And how robust is this? Does it, what conditions do you need to make it really robust, or is it robust? Is it it occurs in some collapses, doesn't in others?
So far, we haven't found. Well, there's we haven't found many cases in which, in other cases, the stronger magnetic field prevented the formation of such a very flat, not quite disc-like, but a bit toroidal structure.
Okay, so here. So nice talk. So I have two questions. So one of them is you show the weak correlation between the explosion energy and the compactness.
Right.
So can you tell us the physical reason why it has such a weak correlation?
Well, pardon me. Right, goes roughly the color coding from blue to yellow across the rainbow is roughly also is actually the mass of the stars. We go from low masses to higher masses, which also, I mean, the picture is a bit muddled by the presence of rotation of magnetic fields. In our cases, the stronger.
So do you think like a neutrino heating account for this one?
Well, it depends a bit. We, in particular, at the higher masses, higher proteinita, mostly higher proteinita masses, and higher explosion energies, we have stronger contributions from rotation of magnetic fields. So this makes the connection compactness to neutrino emission to explosion a bit more complicated. So it adds an additional dimension, I think, to this picture.
So just a quick another question. So you show like a proton neutron star convective layer. So this I'm curious about the magnetic field. Is this has this already reached equipartition?
Not quite. It is. Right. What in this forest of lines I'm showing here is the rotational energy of the different proton-neutron stars and the magnetic energy. So rotational energy is dominating by far. But if we subtract that and only compare magnetic energy to, say, convective energy, we get a bit closer. It's not exactly at equipartition, but much closer than that.
Martin, beautiful work, beautiful presentation. Thank you. Can you, I mean, you have a lot of physics in your simulations, yet you get out to 3 or 4 seconds. Can you speak to the compromises you've made to be able to do that? Because, you know, without those compromises, I don't see how we could get out that far. But so I'd like to hear what was done.
Dirty secret is the still not very high grid resolution. So it's a spherical coordinate system. We get around the CFL condition by using a kind of de-refinement similar to the dendritic grid of Phonox. But other than that, it's a lot of waiting and compromising on the resolution. Grid resolution is not tremendously high.
Okay. This is spectral transport, yes?
It is.
And in the opacity set, what was included? I mean, is it everything, including energy exchanging, scattering on nucleons and things like that?
That's not included.
That's not, but everything else is in there.
The usual set.
The usual set. Okay. Yeah.
Say the Bruin.
The Bruin set, Bruin 85. Okay, great. Thank you.
Martin, the lower right panel, the lower left panel, sorry. The lower left panel is the rotational energy of the neutron star.
Yes.
where does this late time decline come from?
Right.
And what is the explosion energy doing at that time? Or do you lose that energy by energy non-conservation? What's the issue?
Right. This here. There is
Yeah.
indeed a loss of rotational energy and angular momentum for this particular case after a bit more, around 3 seconds. The explosion energy, this is actually this case where the explosion energy goes up late.
So energy conservation is fulfilled?
I hope so. I mean,
I hope you had tested.
yes. Well, not not in the sense that everything that's lost in rotational energy goes into explosion energy. In fact, a lot is lost by neutrino emission. It's not a spin down that's 100%, not near.
Yeah, I
100%.
mean, if you want to convert rotational energy into neutrino emission, you have to first make thermal energy.
Yes.
And that is then some viscous effect, which may be numerical or which may be physical, and also total energy conservation, of course, needs to include the neutrino energy. So my question overall is, how good is energy conservation in those simulations?
I can't give you the number right away.
That's at least a fair statement.
Yeah.
Last question for Matteo.
Thank you. Hi, Martin. So when you talk about neutrinos and luminosities, I think I saw like a sort of an offset between electron neutrinos, electron antineutrinos, which remind me of something we also saw in 2021, which we identified as an effect specific on fast rotation and strong magnetic fields. Is that something that you see systematically in magnetized models, like this difference in between the two species?
Seems to be there.
Because in that case, it really speaks to just the presence, not just of fast rotation, but really the magnetic fields, without which it seems to go away. Do you have like a benchmark without magnetic fields and fast rotation to?
Right, there is a case I haven't included in there. I can show you.
Thanks.
All right, let's thanks again, Martin.